Analysis of graphs. When a frequency or grouped frequency distribution has a large number of intervals, then the corresponding histogram has many vertical columns, such as these. In such a case, we often find that the histogram is replaced by the corresponding frequency curve. This can be formed by drawing a curve going through the midpoint of the top of each rectangle. And often down to the horizontal axis at each end. An example of a histogram on the corresponding frequency curve is shown below. The frequency curve maintains the idea that frequencies are represented by areas under the graph, just like a histogram. Also, comments on statistical graphs apply to both histograms and frequency curves. Part 1. Positions of the mode, median and mean on a statistical graph. We can interpret the positions of the mode, the median and the mean of a distribution on a statistical graph, histogram or frequency curve. The mode. So we know that the mode is the most common. The position of the mode on a graph is at its highest point. So we can see this is the highest point of this graph, so that's where the mode is, the most common value. The mode, like all measures of central tendency, must be a value on the horizontal axis. Recall that the mode of a distribution does not have to be unique. There could be two or more modes. A distribution and its graph, which has two modes, is called bimodal. An example of a bimodal graph is shown opposite. So here's one mode and here's another mode. So it's bimodal, it has two modes. If a distribution and its graph has many modes, it is called multimodal. A distribution with a single mode is sometimes called unimodal or unimodal. So this graph at the top here is unimodal. The median. We know the median is the middle value in a ranked or ordered set of data. The median is at the point where the area under the graph is divided in two. So 50% on each side. So we can see this is the median here because 50% of the area under the curve is to the left of that line and 50% is to the right. By comparing this graph with the unimodal graph shown above or on the previous slide, we can see that the median does not have to be in the same place as the mode. This is important. The median does not have to be in the same place as the mode. The mean. The mean is the point upon which the whole graph would balance if we consider it to be a block of uniform density. The mean is shown opposite as a pivot or a fulcrum under the graph. So if we imagine this was a balance or a pivot, the graph would balance perfectly. This line would be completely horizontal because it would have the same weight on the left as it has on the right. Unlike the mode and the median, the mean is affected by the distance of areas from the middle. Part 2. Shapes of graphs and positions of the mode, the median and the mean. Symmetric graph. A graph is said to be symmetric if it has a vertical axis of symmetry through the middle. For a symmetric unimodal graph, the mode, the median and the mean are in the same place going through the highest point of the graph. So here we have an example. We can see that this line is like a mirror line. We have the exact same shape on the left as we have on the right. So this graph has an axis of symmetry and the mode is equal to the median, which is equal to the mean, and it's at the very highest point of the graph. Positively skewed, also known as skewed to the right. A graph is positively skewed or skewed to the right if the high point is to the left of the graph and there is a significant tail to the right. So we can see this graph here. The highest point is to the left and it tails off to the right. So if it tails off to the right, it's positively skewed. If a graph is positively skewed, then the mode is less than the median, which in turn is less than the mean. So we see the mode would be to the very left, because that would be the highest point of the graph. The median would be to the right of that, and the mean would be to the right of the median. So we'd have mode, median, mean in that order. So in symbols, the median is greater than the mode, and the mean is greater than the median. Negatively skewed, also known as skewed to the left. A graph is negatively skewed or skewed to the left if the high point is to the right of the graph and there is a significant tail to the left. So we can see here the right hand side of the graph, we've got its highest point, and there's a tail to the left. So this is known as left skewed or negatively skewed. So the tail is moving in the negative direction of the x-axis. That's another way to think about it. If a graph is negatively skewed, then the mode is greater than the median, which in turn is greater than the mean. So we can see the mode is to the right. It's the farmost to the right value. It's the highest point of the graph. To the left of that is the median, and to the left of the median is the mean. So in symbols, the median is greater than the mean, and the mode is greater than the median. Or you could say the mean is less than the median, and the median is less than the mode. When a graph is skewed, the mode is at the highest point, the mean is dragged into the tail, and the median is in between the two. This is probably the best way to learn it off. The mode is always the highest point, the mean is dragged into the tail, and the median is in between the two. Learn this off by heart. A large grouped frequency distribution has a mean of 28 and a mode of 34. The distribution is moderately skewed. Part 1. Sketch a frequency curve to represent this data. Because there's only one mode mentioned, the distribution is unimodal, so there's one high point. Because the mean is less than the mode, the frequency curve is negatively skewed. This is shown opposite. So here we have our x-axis and our y-axis. We know we only have one high point, and that's going to be the mode. The high point has to be to the right, and the tail has to be to the left. The mode of 34 is the highest point, and the mean is 28. 28 is obviously less than 34. So we know that this is the direction of our tail because the mean will always lie beside the tail. Part 2. Explain where the median of the data lies. As the median lies between the mode and the median will lie between 28 and 34. So the median is somewhere in here. We don't know what it is. Part 3. Interpretation of standard deviation on a graph. The diagram opposite shows the effect that the standard deviation can have on the shape of a statistical graph. In the diagram, we show the graphs of two distributions, A and B, which have the same mean. But because the graph of A is more widely spread about the mean than that of B, A has a greater standard deviation than B. So graph A, which I've highlighted here in yellow, is more widely spread about the mean. You see the mean is in the center here. So it's much wider spread. Whereas graph B, drawn here in green, we can see the tail ends of graph B are much closer to the mean. So it's not as widely spread as graph A. So A, which is more widely spread, has a greater standard deviation than B. The diagram shows histograms representing four distributions, A, B, C, and D, all of which have a mean of 2.5. Consider the following statements. Part 1, A has the smallest standard deviation. Part 2, D has the largest standard deviation. Part 3, no two of the distributions have the same standard deviation. So we need to answer 1, if part 1 only is true, that A has the smallest standard deviation. 2, if part 1 and part 2 are true, so A has the smallest standard deviation and D has the largest standard deviation. 3, if part 2 and part 3 are true, so part 2, D has the largest standard deviation, and 3, no 2 of the distributions have the same standard deviation. Number 4, if part 1 and part 3 are true. So part 1, A has the smallest standard deviation, and part 3, no 2 of the distributions have the same standard deviation. And lastly, number 5, if all 3 statements are true. So part 1, 2 and 3, if they are all true. So we must first decide which of the statements are true. So statement 1, A has the smallest standard deviation. This statement is true as it has the greatest proportion of its area close to the mean. So remember, the mean is 2.5, which is about here. And we can see that A has most of its bars, or you could say the greatest area of its bars, closest to 2.5. Whereas, on the contrary, B has its highest bars as far away from the mean as possible. If the mean is 2.5, then obviously 0 and 5 is as far away on the graph as we can get. So statement 1, A has the smallest standard deviation, is definitely true. Statement 2, D has the largest standard deviation. This is not true because B has the greatest standard deviation with a huge proportion of its area near the edge. So we can see B, if this is where the mean is, 2.5, we can see that the highest bars are as close to the edge. So B actually has the highest standard deviation and not D. So part 2 is not true. 3. No 2 of the distributions have the same standard deviation. This is not true because C and D have equal spread about the mean. So it doesn't matter how high the bars are, they have equal spread about the mean. If this is the mean, 2.5, we can see that all the bars are the same height either side, as is the case with D. This is the mean, 2.5, and all the bars are the same height either side. So they both have equal spread about the mean, even if their bars are of different height. So hence the answer is 1. Only part 1 is true.